Hi, and welcome to the fourth and final part in this video series on the LINQ technology using C#. This video is also part of the 7th tutorial in an advanced C# course. This video is a continuation of the previous 3 videos in this video series on LINQ, so I recommend viewing the previous 3 videos in this video series before viewing this video. Links to these videos are available below in the description. For more content on advanced C# concepts and much more, please consider subscribing and please ring the bell so that you'll be notified of future content. Just a reminder to please hit that like button if you feel you are benefiting from these videos. Your support is greatly appreciated. Thank you. In the previous video in this series, we looked at code examples where certain LINQ operators were implemented to query and transform data. This video is a continuation of the previous video in this series, where we'll create code examples using some of the other LINQ operators to gain a broader understanding of what can be accomplished using the LINQ technology in C#. So in the previous videos in this series, we have created code examples using the following LINQ operators. The sorting operators, order by descending, and then by descending. The grouping operators, group by and toLOOKUP. The quantifier operators, all, any, and contains. The filter operators, of type and where. The element operators, element at or default, first or default, last or default, single and single or default. The join operators, join and group join. We have already looked at the select projection operator, and we'll also look at the select operator in this video, and in addition to this, we'll also look at the SelectMany projection operator. So in this video, we'll look at the following LINQ operators. The equality operator, sequence equal. The concatenation operator, concat. The set operators, distinct, except, intersect, and union. The generation operators, default if empty, range, and repeat operators. The aggregate operators, aggregate, average, count, sum, and max. The partitioning operators, skip while, take, and take while. The conversion operators, toList, toDictionary, and toArray. And lastly, the projection operators, select and SelectMany. We'll also look at the following keywords that are useful when used in queries implemented in query syntax, namely the let and into keywords. We have looked at the select projection operator already in previous videos, but we'll look at this operator again in this video, as well as look at the SelectMany projection operator. We'll then be able to gain an understanding of the difference between the select and the SelectMany projection operators. As in the previous videos, I'll be demonstrating the code examples on my Mac platform. If you are using a Windows platform to follow along, the experience of creating these code examples will be almost exactly the same. So the fact that I'm using Visual Studio for Mac should not be a barrier for a learner using Visual Studio for Windows to follow along with the creation of these code examples. Okay, so let's create a .NET Core console project. So the official release of .NET 5 has now been released. So I'll be running this project using the new .NET 5 .NET runtime. For more information on the significance of the .NET 5 runtime, please view the second part of this advanced C# course. I've included a link to this video below in the description. The project we created in the last video was named LINQExamples_2. Let's name this project LINQExamples_3. So as we did in the previous video, let's navigate to this URL where we can access code on GitHub for the project that was created in the previous video of this series. Here we can copy the data-related code that we created in our previous project so that we can reuse these data-related classes in this project. Let's click the directory icon labeled link examples_2. Let's then click the file icon labeled program.cs. Let's copy the class named employee and paste the contents of our clipboards to our new project. Let's do the same for the department class. And the data class. Okay, so we won't be using the getHeterogeneousDataCollection method that resides in the data class in this video, so let's delete this method. Let's refresh our memories about the classes we have just copied and pasted from GitHub. The employee class contains a definition for an employee record. The department class contains a definition for a department record. The data class contains hard-coded, made-up data for employee records and department records. The employee records are stored in a generic list strongly typed as employee. The department records are stored in a generic list that is strongly typed as department. We can access the data stored in the employee list collection from calling client code, in this case, this will be the main method, by calling the static method named getEmployees. We can access the data stored in the department list collection by calling the static method named getDepartments. Note that the data class in which these methods reside is a static class. Let's navigate to the main method, and before we create our example code, let's add the appropriate using directives. First, let's add a using directive to the system.collections.generic namespace. The generic list type is a member of this namespace. Let's also add a using directive to the system.link namespace. Once we have added our system.link using directive, we can access our link operators on collection types that implement the IEnumerable interface. So, for example, list types implement the IEnumerable generic interface. So we are able to access extension methods stored within the enumerable static class, which is a member of the system.link namespace, by including a using directive to the system.link namespace. The queryable static class also includes link extension methods and is a member of the system.link namespace. For more information on how extension methods work in C#, please view the first video in this video series. A link to this video has been included below in the description. Before we get started creating our code examples, I want to draw your attention to what might be an issue for Visual Studio for Mac users. When we run our code interactively through Visual Studio for Mac, by default, the output may appear in the terminal console window within Visual Studio for Mac, like this. This is absolutely fine for testing code, but you may prefer to present the output externally, i.e. in a terminal console window outside of Visual Studio for Mac. If you would prefer to present your output externally, i.e. outside of Visual Studio for Mac, please navigate to Visual Studio for Mac Preferences, then under the heading marked Other, select the item labeled Terminal. In the right pane of the relevant dialog box, ensure that the Enable Integrated Terminal checkbox is unchecked. This is obviously not a functional issue, it really comes down to personal preference. Let's define a generic list variable named EmployeeList that is strongly typed as employee, and let's assign the collection of employee records returned by the data.getEmployees static method to the EmployeeList variable. Let's define a generic list variable named DepartmentList that is strongly typed as department, and let's assign the collection of department records returned by the data.getDepartment static method to the DepartmentList variable. Okay, so we are now ready to query and transform data using LINQ. So let's start with the equality operator, sequence equal. So the use case here is we want to compare two lists of data, and we want to know if these two lists contain elements of equal value and each element in each of the relevant lists are stored in the same order. If each item in each list matches in terms of value and order, the sequence equal method will return true. If any of the items in each of the relevant lists does not match in terms of value and order, the sequence equal method returns false. Let's create a generic list named integer list1 that is strongly typed as integer. Let's copy and paste this line of code to the next line. Let's change the name of the second list to integer list2. Let's run the code. And the sequence equal method returns true, because the values and sequence of elements in integer list1 is identical to the values and sequence of elements in integer list2. Let's change the order of the items in integer list2 so this sequence of values is not equal to the sequence of values stored in the list named integer list1. Let's run the code, and this is an expected result. Let's change integer list2 once again for good measure. And this is an expected result. Great. So let's change the data in integer list2 so that the order and values in the lists are equal. And now the result is true, which is an expected result. That was pretty straightforward, i.e., comparing two sequences of values of a primitive data type, i.e. the integer data type. But what if we want to test this type of equality between two lists that are strongly typed with a complex type, like for example our employee user defined type? So let's define a variable named EmployeeComparer as a generic list type that is strongly typed as employee, and let's assign the collection returned from the data.getEmployees static method to our EmployeeComparer variable. Let's run a sequence equal operation and compare the values stored within our EmployeeComparer collection with the values stored within the employee list collection. So one would expect the result of this sequence equal operation to return true because both collections contain exactly the same data. Let's see what happens. Oh, and false is returned. The reason why false is returned is because we need to tell the compiler how to establish equality between objects of the relevant complex type, i.e. in this case, the employee type. So we achieved this in the previous video in this series by implementing the built-in EmployeeComparer generic interface. So let's copy the relevant code for this that we implemented in the previous video in this series. Let's navigate to the GitHub repository at this URL that contains the code we created in the previous video in this series. Let's copy the class named EmployeeComparer to our clipboards and paste the contents of our clipboards to our projects like this. We have red squiggly lines, so let's fix this by bringing in the appropriate using directive. So here we have implemented a class named EmployeeComparer that implements the generic EmployeeComparer interface that is strongly typed as employee. This gives us a way of telling the compiler how we want objects in our lists of type employee to be compared when determining equality between the relevant objects. So we are explicitly doing this here in the equals method, where we are comparing the ID, first name, and last name properties between two employee objects. We are returning true if the relevant properties of the relevant two objects are equal, and false is returned if any of the relevant properties of our two objects are not equal. Within the getHashCode method, we are returning the hashcode of the ID property of the relevant employee objects. For more information on hashcodes, please navigate to this URL. So now let's go to our main method, and we can pass in a new instance of the EmployeeComparer class to an overloaded version of the sequence equal method. This object will tell the compiler explicitly how we want our employee objects to be compared. Let's run the code. And now the sequence equal operator works as expected. So note that we need to tell the compiler how we want objects that are defined as complex types to be compared when determining equality between the relevant objects. We can do this by creating a class that appropriately implements the EemployeeComparer generic interface. Great! Let's move on to the concatenation operator named concat. We can use the concat operator to append one collection of data to another collection of data. So let's see the concat operator in action. Let's create a collection of integer values. Let's then create another collection of integer values. Let's append the second collection of integer values with the first collection of integer values using the concat operator. Let's write code to output the results of this concatenation operation to the screen. Let's run the code. Great! Let's do another example, but this time let's append a collection that contains a collection of objects of a complex type to another collection of objects of the same complex type. The complex type we'll use in this example will be our employee user-defined type. Once again, we can use the concat operator to achieve what we want here. Let's run the code. Great! Let's move on to the aggregate operators. Let's first look at the aggregate operator. Using the aggregate operator, we can perform a custom operation on values within a collection. Let's say we have a requirement where we need to provide a total for the annual salaries of our employee records. We also need to include the addition of an appropriate annual salary bonus in the final result. Let's say a manager gets a bonus of 4% and employees that aren't managers get a bonus of 2%. So let's say we have a use case where we need a result that is a total of all employee annual salaries, which must include each employee's bonus. We can take this added complexity into account when totaling up our employee annual salaries through the use of the aggregate operator. So the first argument is the seed value. So let's provide 0 for this argument. Using this argument, we are initializing the value that will be returned by our aggregate operator. The next argument is of a delegate type, where we can include the logic for our aggregation functionality in the form of a lambda expression. So as you can see in our logic for the relevant lambda expression argument, we are checking to see if the relevant employee is a manager, whereby we need to add a bonus of 4% to the relevant employee's annual salary. If the employee is not a manager, we need to add a bonus of 2% to the relevant employee's annual salary. We can then include the appropriate bonus amount in our calculation. So we are adding up all employee annual salaries, which includes each employee's appropriate bonus. Let's run the code. Great! Say we want to output a comma-delimited string from our employee list collection. Each delimited item containing the employee full name, a dash, then the employee annual salary. Each annual salary must include the appropriate bonus. We also want to include a label preceding the comma-delimited string. We can achieve this using the aggregate operator like this. The first argument is the label, where an appropriate value could be something like employee annual salaries including bonus. Then the logic of our aggregation functionality can be expressed in a lambda expression for the second argument, like this. We can apply the same logic to include appropriate bonuses from our previous example. Let's run the code. Great, but we have a slight issue where a comma is presented at the end of our string. We don't want this comma in our final result. We can express this by passing a lambda expression as our third argument to an overloaded version of the aggregate operator. This argument allows us to perform a final operation on the results produced by the lambda expression passed in as the second argument. We first need to include another datatype argument with an angle brackets following the aggregate method to declare the datatype of the final output, i.e. provided by the lambda expression we are passing in to the last parameter of this overloaded version of the aggregate method. In the lambda expression passed in as our final argument, we are using the substring method to remove two characters from the end of the result, which means a comma and a space will be removed. This result is what we want. Excellent. So let's move on to the average aggregate operator. So to find the average annual salary for a list of employees, we can apply this code. Great. If we want to find the average salary for all employees in the technology department, we can use method chaining and the where operator to achieve this, like this. Great. For more information on method chaining, please view the second part of this video series. Let's move on to the count aggregate operator. So if we want to know how many employee records we have in our collection of employee records, we can apply the count operator like this. Great. If we want to know how many employees are members of the technology department, we can pass in a condition as an argument to the count operator. The condition that is passed in as an argument to the count method can be expressed in the form of a lambda expression. Great. Let's move on to the sum aggregate operator. So let's keep this simple. We just want the sum total of all annual salaries of all employee records stored in our employee list collection. We can apply the sum operator to achieve this. Great. Let's move on to the max aggregate operator. So if we want to return the highest annual salary property of all employee records stored in our employee list collection, we can apply the max aggregate operator in a LINQ query like this. Great! Let's move on to the generation operators, namely default if empty, empty, range, and repeat. Let's first look at the default if empty operator. So we can use the default if empty operator to return a new IEnumerable collection that when, for example, we apply the element at method on the new collection to check if the new collection is empty, the operation will return the default value for the relevant type used to strongly type the relevant collection. A query using, for example, the element at method against a collection returned from a default if empty operation will not throw an exception if the collection is empty. The default value of the type with which the relevant collection is strongly typed will instead be returned. For more information on default values for C# data types, please navigate to this URL. We'll see later how we can pass in a value to the default if empty method to specify our own default value that we'd prefer to be returned when, for example, the element at method is used to check if the relevant collection is empty, rather than the default C# value for the relevant data type. Let's look at an example using the default if empty method. So let's create an empty list of integer values. Let's perform a default if empty operation on this collection of integer values and assign the returned collection to a new collection of integer values. Let's use the element at operator and pass in 0 to the element at method to check if the collection is empty. you can see that the element at operator returns the default value for the integer data type, which is 0. This is an expected result. Let's create another example, but this time let's use the employee data type to strongly type our collections. As discussed, the default value for a reference type in C# is null. But as discussed, we can pass in a default value that we would prefer to be returned by, for example, the element at operator when the relevant collection is empty. So let's pass in an employee object where the ID property of the relevant employee object is set to 0. Null is not returned, as would be the case if we hadn't passed in a value to the default Fmt method, because we have specified our own default value where the ID property of the default employee object is 0. Great. Similarly, we could have set the default value for our integer collection example by, for example, passing in 999999 to the default Fmt method. Instead of returning the default C# value for an integer, which is 0, 999999 is returned. This is an expected result. Excellent. Right, let's look at the empty method. So we can use the empty method to generate a new empty collection. So for example, we want to create a new IEnumerable generic collection of employee records. We can do this by using the empty operator like this. Note, the empty method is not an extension method of IEnumerable or IQueryable like other LINQ methods. It is a static method included in the enumerable static class. So for example, we could instantiate a new empty generic list strongly typed with the employee user-defined type through the use of the empty method. We can then chain the toList conversion operator to this operation and return an empty generic list. We are using the toList operator to convert an IEnumerable generic collection that is strongly typed with the employee data type to a generic list that is strongly typed as employee. So for good measure, let's add a new employee item to our new list that we have generated through the use of the empty method and the use of the toList conversion operator. Let's write code to write the items, or in this case one item, stored in our new list to the screen. Great. Right, let's move on to the range generation operator. We can use the range operator to return a collection of values that are within a specified range. So let's clarify this with an example. We want to return a range of integer values in a collection where the first item in the range has a value of 25 and each subsequent item is incremented by a value of 1 until there are a total of 20 values in the relevant collection. We can achieve this by using the range method like this. In this example, the first argument specified is 25. This is the value of the first element, and the second argument specifies the number of elements to include in the relevant generated collection. When each item is added to the collection, it is incremented by a value of 1. So the second item will be 26, the third item will be 27, the fourth item will be 28, and so on. Let's run the code. Great. So using the range operator, we have generated a collection of integer values that fall within a specified range. Excellent. Let's say we want to generate a collection of a specified amount of elements where a value for each element in the collection is repeated. We can use the repeat operator for this purpose, like this. Great. Let's move on to the set operators, namely distinct, except, intersect, and union. Let's start with distinct. So let's say we have a strongly typed generic list that contains a list of integer values, some of which are repeating values. We want to perform a query against this list of integer values where we only want distinct values returned. We can achieve this by applying the distinct operator to our query like this. Great! Let's say that we have two collections of a specific type and we want to return elements with values in our first collection that are not equal to any of the values of the elements in our second collection. We can achieve this by using the except operator. Let's look at an example of using the except operator applied to two collections of integer values. So 1 and 2 are returned in our results collection because these values exist in our first collection and don't exist in the second collection. The values 3 and 4 exist in our first collection and also exist in our second collection. The values 5 and 6 exist in our second collection, and even though these items don't exist in our first collection, the except operator does not return these items as part of the results collection, because in this example, the except operator returns values that exist in the first collection and don't exist in the second collection. Let's try an example using complex types. Let's use our employee type. Let's create a generic list strongly typed as employee. Let's copy data that we know will exist within our employee list collection and add these items to the list we have named employee list 2. Let's add some additional items to the employee list 2 collection. Let's then call the except method on the employee list collection and pass in the employee list 2 collection as an argument to the except method. Then let's assign the results of this operation to an implicitly typed variable named results. We have of course used the var keyword to implicitly type our results variable. Let's write code to traverse the results and output the results to the screen. Let's run the code and see what happens. And this result is not expected. The output contains all items within the employee list collection. I would have expected that the items that were copied from the data class and added to the employee list 2 collection, as well as the other items that we added to the employee list collection, would be excluded from the results. The reason for the unexpected results is because we have not told the compiler how to compare employee objects when determining if one employee object is equal to another employee object. So how can we let the compiler know how we want one employee to be compared to another employee within our collections when determining equality between the two relevant objects? You may have guessed already how we can achieve this. We first need to create a class that implements the EmployeeComparer generic interface. We can then write code to establish how one employee object should be compared to another employee object when determining equality between the relevant objects. We have already included the code for this, which we applied when we created code to perform a sequence equal operation on two lists that were strongly typed as employee. So we have our class named EmployeeComparer that implements the EqualityComparer generic interface. So we can reuse this class for our example that performs an accept operation on two generic lists that are strongly typed as employee. So all we need to do is create a new object of type EmployeeComparer and pass this object into an overloaded version of the accept method like this. Let's run the code. Great! This is now an expected result. Let's move on to the intersect operator. So we can use the intersect set operator to return a collection containing only those items that exist in the employee list collection that are equal to the items that exist within the employee list 2 collection. And now that we know we are comparing elements in two collections that are strongly typed with the employee complex type, we need to pass in a new object of the EmployeeComparer type, i.e. a type that appropriately implements the generic IEqualityComparer interface. This tells the compiler how to compare two objects of type employee when determining if the relevant employee objects are equal. Let's run the code. And this is an expected result. Great. Let's move on to the union operator. The union extension method requires two collections and returns a new collection that includes distinct elements from both the collections. We can again use the same data we have used in the previous two examples to test the union operator. Right, let's write the code for this. You will notice we are also passing in an object of type EmployeeComparer to the union method. Let's test the code. Great! So let's see what happens in this example when we don't pass in an object of type EmployeeComparer to the union method. You can see that duplicate records are included in the results as a consequence of not passing in an object derived from a class that appropriately implements the generic IEqualityComparer interface. And of course, we know we have already created such a class. So let's ensure that we pass in our object of type EmployeeComparer to the union method so that only distinct employee objects are included within our results. Excellent. So let's move on to the partitioning operators. These partitioning operators include the skip, skip while, take, and take while operators. Let's first look at the skip operator. Use the skip operator to skip over a given number of elements in a sequence and then return the remainder. So let's query our employee list collection using the skip operator. Let's skip over two of the elements stored in our employee list collection and return the remainder of the elements using the skip operator. Great, this is an expected result. Let's look at the skip while operator. Using the skip while operator bypasses elements in a sequence as long as a specified condition is true, and then returns the remaining elements. Let's see this operator in action. So the condition here is skip elements in our sequence of employee objects in the employee list collection while the relevant employee object's annual salaries are above 50,000. Great, this is an expected result. Just to make things a little bit more clear on how this operator works, let's add a new employee record to the employee list collection. This employee record has an annual salary of 100,000, which of course is above 50,000. Let's run the code. And you can see that while the condition is true, the items in the relevant collection are skipped, i.e. will not be returned from the query. However, all subsequent elements in the sequence will be returned once the condition returns false. Even though the last element in the relevant sequence has an annual salary property greater than 50,000, it is still returned, because the third element in the sequence caused the condition to return false. The fact that the last element has an annual salary above 50,000 and therefore causes the condition to be true doesn't mean that the last item will be returned by our query. Note that once the condition returns false, all items from that point will be returned from our query. Right, let's move on to the take partition operator. The take operator is used to return a specified number of contiguous elements from the start of a sequence. Let's see this operator in action. This is an expected result. Great! The first two elements in the relevant sequence of elements in our employee list collection are returned by our query. So let's move on to the take while partitioning operator. The take while operator returns elements from a sequence as long as a specified condition is true, and then skips the remaining elements. So let's use the same condition that we used in the skip while operator example. So here we are using the take while operator to return elements from the relevant sequence that have an annual salary above 50,000. So the first two elements in the sequence are returned by our query. As soon as the third element is evaluated and the condition returns false, the elements from that point onwards in the relevant sequence will not be returned by our query. So for example, the fact that the fifth element in the employee list collection has an annual salary property that is greater than 50,000 is irrelevant, because when the third element causes the condition to return false, and in terms of the take while operator this means that from that point onwards, the rest of the elements in the relevant sequence will not be returned by our query. Great! Let's look at the conversion operators toList, toDictionary, and toArray. So let's look at the toList conversion operator. A query written in query syntax will return an IEnumerable collection containing the results of the query. What if we need our results to be returned as a generic list? We can achieve this using the toList conversion operator. Let's create an example to clarify this point. So for this example, let's query our employee list collection for employee records that have an annual salary property greater than 50,000 using query syntax. Note the red squiggly lines here. This is because we are attempting to assign an IEnumerable collection to a variable of type generic list. The compiler is telling us that we have created a type mismatch. So we can use the toList operator to convert the IEnumerable collection returned by our query to a generic list by wrapping the relevant query in brackets, adding a dot after the last bracket, and applying the toList operator like this. So now you can see the red squiggly lines disappear because we have removed the type mismatch. Let's run the code. Excellent. As discussed earlier in this video series, wherever a toConversion operator is applied to a query, as we have done here, this causes the query to execute immediately, i.e., query execution is not deferred, it is executed immediately. So if we want to convert an IEnumerable collection returned from a query to a dictionary object, we can apply the toDictionary operator to the query. Let's create an example to clarify what is meant by this. So, as in the previous example, here we have a standard query written in query syntax to query our employee list collection for all elements where the relevant elements have annual salary properties that have values greater than 50,000. So this is a basic query that will return an IEnumerable collection. But what if we want to return a collection where each element has a unique key associated with the relevant element? We can do this by converting the query result to a dictionary generic collection type. So let's alter our code so that the IEnumerable collection returned by our query is converted into a generic dictionary collection. So within angle brackets after toDictionary, we need to pass in two data types. The first data type declares the data type of the value stored in the dictionary. The second data type declares the data type of the key that will be used to uniquely identify each element in the collection. So the first data type is of type employee, and the second data type is of type int. Note that we want each element to be keyed on the employee ID property. We can express this by passing in an appropriate lambda expression to the toDictionary method like this. So let's traverse the key values stored in our dictionary object using a for each loop. Note how we are able to use the key values to retrieve the values of each element stored in the dictionary. We are doing this by passing in the relevant key within square brackets to the dictionary object. Here we are outputting the key as well as each employee's first name and last name to the screen. And as you can see, we have each employee's ID, which we have designated as our key value, followed by the corresponding employee's first name and last name properties. Excellent. We have successfully converted a query result from an IEnumerable collection to a dictionary object. As discussed, when we call any of the two conversion operators on a query result, this causes our query to execute immediately. For more information on deferred execution versus immediate execution, please view the second part of this video series. For good measure, let's also create a result using the toArray conversion method. So if we try to assign the results of this query to a variable defined as an array of employees, the compiler complains of a type mismatch. The query result is returned as an IEnumerable collection and not an array of employee objects. To remove the type mismatch, we can apply the toArray method like this. Great. So let's discuss the let and the into clauses that can be applied when using query syntax to represent a LINQ query. Let's look at the Microsoft Docs for an overview of the let clause. This overview of the let clause can be found at this URL. In a query expression, it is sometimes useful to store the result of a sub-expression in order to use it in subsequent clauses. You can do this with the let keyword, which creates a new range variable and initializes it with the result of the expression you supply. Once initialized with a value, the range variable cannot be used to store another value. However, if the range variable holds a queryable type, it can be queried. So let's look at a basic example using the let keyword in a LINQ query. Let's say we wish to query our employees based on employee initials. Now we don't have an initials property for an employee record, but within our query, using the let keyword, we can extract the initials from each employee record's first name and last name properties and assign the result of this extraction process to a variable named initials, directly within our query using the let keyword. This allows us to use the initials variable in our where clause as well as reuse the initials variable within our select clause. Through the use of the let clause, we can also apply a condition, and based on the evaluation of that condition, store a value in a variable that can be used later in the query, like for example within a where clause. Here we have a condition where we need to add an appropriate bonus to the annual salary property, based on whether the employee is a manager or not a manager. If the employee is a manager, we need to add a bonus of 4% to the relevant employee record's annual salary property. If the employee is not a manager, we need to add a bonus of 2% to the relevant employee record's annual salary property. We can store the relevant annual salary plus bonus value for each employee record by assigning the value returned by a ternary operator to a variable. We have named this variable annual salary plus bonus. The let clause in this example enables us to reuse the annual salary plus bonus variable, both within the where clause and the select clause later in the query. Let's run the code. Excellent. Let's look at the into keyword. We can use the into keyword in a LINQ query to collate data within a group, and then after this operation, we are able to perform a filter operation within the same query, if required, on the grouped data through the use of a where clause. So for example, let's use a LINQ query to first create a group of high-earning employees based on a condition. Let's say that the employee must earn above $50,000 to fit into the relevant group. We can use the where clause at this point in the query to appropriately filter the relevant employee records and the into keyword to put the filtered data into the relevant group of high-earning employees. So we can use the into keyword to group the high-earning employees into a group named high earners. Let's say we then want to further filter this group of high-earning employees by management status. So we only want these employee records where the isManager property is set to true returned from our query. We want to know which of those high-earning employees are managers. So we can use another where clause within our query to filter the high earner group based on the relevant condition. We have used a where clause earlier in our query to create the group of high earning employees. Then once the group is created through the use of the into keyword, we can further filter the group of high earning employees based on each employee record's isManager property. So we are able to include another where clause in our query to filter the grouped data. Let's run the code. Great. So lastly, let's look at the select and the SelectMany projection operators. In this video series, we have already looked at the select projection operator. So the focus in this example is on the SelectMany operator. We want to know how it differs from the select operator and in what circumstances we may wish to apply the SelectMany operator in a LINQ query. Let's navigate to a Microsoft Docs webpage to see what the Microsoft Docs say about these two projection operators. Projection refers to the operation of transforming an object into a new form that often consists only of those properties that will be subsequently used. By using projection, we can construct a new type that is built from each object. You can project a property and perform a mathematical function on it. You can also project the original object without changing it. Select projects values that are based on a transform function. SelectMany projects sequences of values that are based on a transform function and then flattens them into one sequence. To understand the difference between the SelectMany operator and the select operator, let's modify our department class so that it includes a property that stores a collection of employees. We have already discussed that department records have a one-to-many relationship with employee records. So each department object will now store a collection of related employee records. Let's also alter the getDepartments static method that resides in the data static class so that the getDepartments static method accepts an argument containing a collection of employee objects. Then for each department object added to the department list collection within the getDepartment static method, let's include a query to return an appropriate collection of employees, i.e. those employee records that have a department ID property matching the ID property of the relevant department object. So let's go to the main method and pass in the collection of employees to the getDepartment method. So now the getDepartments method will return a collection where each department contains a related collection of employee records. So now, what if we want to query the department list collection for all employees? We can achieve this using the select operator, but when traversing the results of the select operation, we will need to use an outer and an inner for each loop, like this. In this scenario, the SelectMany operator is better to use for this purpose. The SelectMany operator is better in this case because we can use one for each loop to traverse the results of our query, unlike where we needed to use an additional nested for each loop to traverse the results of our query, where we used the select operator. Behind the scenes, as it were, the SelectMany operator appropriately flattens the results. And this means we don't need to use a nested for each loop to traverse the results of our query. We are able to use one for each loop for this purpose. Excellent. So we have covered a lot of ground in this video series on LINQ operators. I would encourage you to practice using these operators to become proficient in writing LINQ queries. This is a very powerful technology and is used with Entity Framework to perform database queries in modern .NET applications. Entity Framework is now the recommended technology to use in .NET for implementing database-related functionality in .NET applications. If we navigate to this Microsoft Docs webpage, we can see this paragraph that states, Entity Framework Core is a modern, object-based mapper for .NET. It supports LINQ queries, change tracking, updates, and schema migrations. EF Core works with many databases, including SQL Database, on-premises and Azure, SQLite, MySQL, Postgres, and Azure Cosmos DB. This makes LINQ a very important technology to learn for .NET developers. LINQ enables developers to write one set of code that can be applied to handle data-related functionality for multiple different data sources. In LINQ, expression trees are used to represent structured queries that target sources of data that implement the generic iQueryable interface. If you would like to delve deeper into expression trees, please navigate to this URL. So let's summarize what we have learned in our 4-part series on using the LINQ technology in C#. In the first part of this video series, we created our own extension method to filter data. We also demonstrated how a lambda expression can be used to express a condition that can be passed into our extension method to filter the data and return the filtered results from a query. The reason we created the filter extension method is because LINQ is mostly made up of extension methods stored in 2 static classes, namely a static class named enumerable and a static class named queryable. We are able to access the extension methods within these static classes by including a using directive to the system.link namespace. The enumerable and queryable classes are both members of the system.link namespace. In the second part of this series, we demonstrated examples using the select, where, join, and group join operators. We also discussed the difference between when a query is executed with deferred execution or immediate execution. We discussed how a LINQ query is executed with deferred execution but we can make the LINQ query execute immediately by applying a to-conversion operator to the query. For example, to-list, to-dictionary, or to-array. In the third video in this series, we demonstrated code examples using the following LINQ operators. Sorting operators: order by descending, and then by descending. Grouping operators: group by and to lookup. Quantifier operators: all, any, and contains. Filter operators: of type and where. Element operators: element at or default, first or default, last or default, single or default. In the fourth and final video in this series, we demonstrated code examples using the following LINQ operators: the equality operator, sequence equal; the concatenation operator, concat; the set operators, distinct, except, intersect, and union; the generation operators, default if empty, range, and repeat operators; the aggregate operators, aggregate, average, count, sum, and max; the partitioning operators, skip while, take, and take while; the conversion operators, to-list, to-dictionary, and to-array; projection operators, select, and SelectMany. In this video, we also looked at code examples using the let and the into keywords. I hope you have enjoyed this video series on using the LINQ technology in C#. The next tutorial in this advanced C# course will be on C# attributes. I may take a small break from the advanced C# course in order to create other related videos that I think you'll enjoy. However, rest assured I will complete the advanced C# course once these other related videos have been released. For more content on advanced C# topics and much more, please consider subscribing, and please ring the bell so that you'll be notified of future content released from this channel. If you feel you have gained value from this video, please hit the like button. It will be greatly appreciated. Please feel free to share this video with anyone you feel may benefit from its content. I really enjoy reading your comments, so please feel free to share your thoughts with me in the comments section. All code created in these tutorials can be downloaded from GitHub. A link to the relevant GitHub repositories are available below in the description. Thank you and take care.